All right, here we are again. I guess let's do it. So today we're going to talk about applied optimization and Newton's method. Um, so we'll see how much you remember about optimization. If you want to try this on your own, otherwise I'll walk you through it. But remember the general gist of optimization, in case you forgot and you want to try it on your own, is you read the problem, and in this case, we want the largest area. So you're going to find an equation for area, um, and you're going to find the absolute maximum of that. Now, often there's a constraint. In this case, we know we only have 2,400 feet of fencing to work with. So maybe there's a way you can rewrite the area in terms of just one variable. Right now, area is x times y. Can you put it in terms of only one variable to make it easier to find their derivative of? So, anyway, there's a little hint. You want to try it on your own? Feel free. Otherwise, I'm going to go ahead and explain it. So, the farmer, sorry, the farmer has 2,400 feet of fencing. So, this red part is going to be 2,400 feet. And he wants the largest area. So we know area is x times y. This is called our objective equation because our objective is to maximize this. The constraint is the 2,400 feet of fencing, so we know that 2x plus y has to be 2,400, and we can easily solve that for y. So if I replace y with that, we can get the area in terms of only x, and much easier to find the derivative of. So we find the derivative. So here's the derivative. Find the critical numbers. This will never be undefined, and it will equal 0 when x is 600. Now we need to identify an absolute max. And if we go back to the picture, obviously x can't be any smaller than 0. And if there's two x's and we have 2,400 feet, x can't be any bigger than 1,200 feet. So we have two endpoints for our domain, and we have this critical number. So to find an absolute max, we can easily just make a table of values. And using this formula for area, we can calculate the area at these three values, and we can obviously see the area is maximized right there. So this is one way you can justify if you have endpoints to your domain. We'll look at a second example, how you justify an absolute max versus a relative max when you don't have endpoints. But this just pretty much says what we were just talking about up there. I need to find a value for y. And be careful about saying, just putting your answer as a 600 by 1,200 foot field, because you need to specify specifically the lengths that are perpendicular to the river and the length that's parallel. So make sure you know which one's which. So when you're giving your answer, you kind of have to be wordy about it. So if the farmer makes a field 1,200 feet on the sides parallel to the riverbank and 600 feet on the sides perpendicular to the riverbank, he will maximize the area. So there you go. All right, so there's that example. Here's another one if you want to try this on your own. Pause the video, give it a shot, and we will go ahead and look at it in just a second together. All right, so the idea behind this one is pretty similar. Just the numbers become a little more complicated, honestly. We're trying to minimize the cost, so that means minimizing the surface area. And here's a formula for surface area. The constraint is that volume is 1 liter. And remember that 1 liter is 1,000 cubic centimeters. And the height, if we go ahead and solve this equation for h, we get this. So I can replace this h with this and get area just in terms of r. So here I am replacing h. I rewrite it, find the derivative, and then I got to find the critical numbers. So I went ahead and put this in a single fraction. Where the denominator is 0 is where it's undefined. Where the numerator is 0, that's where we're going to have another critical number. So we have two critical numbers here. Now in this case, there really is no minimum value or maximum value for the radius. The radius can be as big as we want. We're trying to minimize the area, so of course we don't want it too big, but in the grand scheme of things, like as far as just the domain of what the radius can be, we don't have a max value. So how can I justify an absolute max when I don't have endpoints to my domain? So we can go ahead and make a sign chart instead. Put these on there. Notice I didn't bother putting anything in here because this is just outside of the domain. And by the way, I got the sign chart pretty easily. The denominator is always positive because r is squared, so the sign is all based on the numerator. The numerator is a cubic function. End behavior is down on the left and then up on the right, so it has to be negative and then positive. So here, I mean, I'm saying it down here in words, but whoops. Basically, if you look at this, within the domain, area is always decreasing to the left of this critical number and always increasing to the right of this critical number. Therefore, this has to be an absolute minimum. Now, you can't just use the sign chart, though. Again, you've got to say that in words. So that's why I say always increasing to the right, always decreasing to the left. So it reaches a minimum at that point. You're going to have to say those words. You're going to have to write down some sentences for these. So that's R. Now I have to find H. And H, through some manipulation, we can get this, which notice is just twice the radius. So the cost will be minimized when the radius is the cube root of 500 over pi centimeters, and the height is twice the radius. So there you go. So that's optimization in a nutshell. Now let's talk about Newton's method. All right, Newton's method. So Newton's method, the whole purpose is to approximate roots to a function. So what's going on here? Let's say that we have a function here, and I want to approximate this value. Here, I'm actually going to zoom in. I want to approximate this value. So Newton's method is an iterative process. It repeats the same process over and over again, refining the answer each time. So you start with about value. We call this the seed. And you find the corresponding y value on the function. And then you use the tangent line. And you find the root of the tangent line. And then you do it again. Find the corresponding y value, find the tangent line at that point, and notice every time we're getting a little bit closer to our actual value. So that's how it works. So what could go wrong? Well, there's a few things that could go wrong. One is, let's say that your seed that you happen to pick just so happens to be where there's a horizontal tangent line. So it never intersects. You never get a new value of x. If that happens, just try a different value. So that's an easy fix. If the values diverge, so let's say like we have this example here. I want to find this value. I started over here. I'm going to zoom in on this one. I started over here. There's my corresponding y value. I find the tangent line. That's where it intersects the x-axis. I find a new y value, find that tangent line. You can see that these values are just going to get me further and further away from where I want to be. And so if that happens, if you find that your values just increase or decrease without bound, they don't seem to be approaching a number, pick a new value. And then finally, you might have something like this, where you just wind up in an infinite loop. I start here, find my y value, there's my tangent line, there's my new x. My y value, my tangent line, but it takes me right back to where I started. So I just wind up in this infinite loop. If that happens, likely Newton's method won't work. It's happening because we happen to have symmetry right here. And most likely this is a function that is symmetrical about that 0. And if it's symmetrical about that 0, Newton's method isn't going to work. Okay, so that's what could go wrong. Let's try it now. Let's see how Newton's method actually works. Um, First of all, if you ever forget it, it's pretty easy to derive. You start with the equation for the tangent line, and then remember that we're trying to find the x-intercept of the tangent line, so we're going to let y equal 0. And then if you just take this equation here and solve for x, you get that. And that's essentially Newton's method. The a's just change and we get this. So the next value of x is using the current values of x like this. So there you go. There's Newton's method. So let's try one. So if you want to try Newton's method on your own, see if you remember how to do it. Try to use 3 iterations of Newton's method to find a root of this function using x naught equals 1 as your seed. And oftentimes, I don't know if you learned last year, oftentimes when you're doing this by hand, making a table to kind of keep track of all the numbers, you don't have to, but it's highly recommended. I will tell you on my test, I'm going to give you something that you're going to have to do by hand without a calculator. The numbers will be manageable without a calculator, I promise. But I need to see what you are thinking. So if you do not make a complete table like this with everything labeled very clearly, I have to at least see the equation that you're using. And I will tell you that it's easy when you're, even though I'm going to make the numbers manageable, it's easy to make a silly mistake. If you don't make a table like this on the test and you make a mistake, even though I'll see your formula you're using, it may be hard for me to figure out what you did wrong. So I highly recommend showing as much work as you can so I can give you as much partial credit as I can. All right. So anyway, enough blabbering. If you want to try it on your own, go ahead. And here's the solution right here. So sometimes it's helpful to just have these visuals. We have the function right here, x squared minus 2. The derivative is just going to be 2x. So when you start with 1, then 1 squared minus 2 is negative 1. 2 times 1 is 2. Make a fraction out of these is negative 1/2. And 1 minus negative 1/2 is 3/2. And you just do it all over again. Notice 3/2 becomes your new value, and you do it again. 3/2 squared minus 2 is 1/4. 2 times 3/2 is 3. 1/4 over 3 is 1/12. And 3/2 minus 1/12 is 17/12. And by the way, when I say numbers manageable, I could give you something like this problem on the test, but maybe making you only go 2 iterations. I wouldn't make you go this third one by hand, but it wouldn't be that hard. But anyway, a third one gives you right here. And so there's our approximate value. Let's try one more, just so you can see another way of using Newton's method. And then I'm going to show you something on the calculator. Oh, by the way, for fun, remember, we only did 3 iterations. On a calculator, when I divided, this was all the digits the calculator showed me. Square root of 2, here's all the digits it showed me. Not bad. 1, 2, 3, 4, 5 digits after the decimal point. Pretty good estimate. All right. Anyway, try this one. And a little hint, because right now, remember, Newton's method is to find roots of a function. This is not a function. This is just a value. So you need to find a function that has this as one of its roots. You can pause the video now or not. All right, here we go. So we define that function. If you let this value equal x and then basically try to make it equal 0. I mean, I could subtract, just subtract right now. However, that's not a very interesting function. Like, if I just went ahead and subtracted and said this was my function, f of x, is x minus the fourth root of 10. It's kind of assuming I already know the answer. So not the best one to use. That's why I went ahead and did this. I turned it into a polynomial. Polynomials are easy to work with. That's what we generally try to do with these. All right, so this time I didn't tell you where to start. So we need to find that. Now we know the fourth root of 1 is 1, and the fourth root of 16 is 2. The fourth root of 10 has to be in between these somewhere. It's got to be in between 1 and 2. It's probably going to be closer to 2, but do I start with 1 or do I start with 2? And just for fun, I showed you both. Here it is starting with 1, and I also didn't tell you how accurate to make it, so I basically just chose 5 digits. And I just kept going until the first 5 digits didn't change. When starting with 1, it took 7 iterations to get it so that the first 5 digits after the decimal point didn't change. Starting with x equals 2, it only took 4 iterations. So we are estimating the fourth root of 10 is about this. All right, so that's basically the notes, but I do want to show you something on the calculator. I'm going to show you how to do this very easily on the calculator, so when you're doing your homework. But again, know how to do it by hand so that when the time for the test comes. Sorry I don't have the exact calculator. I don't have my program here at home that emulates the calculator exactly, but this is actually really close. This is a free app, by the way, Calculate 84, I think the name is. It's free on the App Store. Okay, first thing I got to do is I'm going to go into y equals, and you can see I've already typed in the function x to the fourth minus 10. So make sure you put the function in. I'm going to quit. Oh, second quit. All right. Now when I'm here, I don't think you can see my button presses very easily, but I will try to be very slow and also tell you what I'm pressing. But I'm going to first start with a seed value. Let's just go ahead and start with 1. I could remember we said x equals 1 or x equals 2 for a seed value. I'm going to do 1 and store that into x. So remember it's 1. Whoops. Yeah, it doesn't. 1 store. Let me do this again. I'm going to have to do it quicker. The store you can see is next to the 1 key. It's got STO, STO. So 1 store x. And I hit enter. And now the calculator knows x is 1. So now that I got that, I'm basically going to type in Newton's method's formula. It's going to look kind of weird in places, but just kind of go with it. So remember, Newton's method formula says that we're going to take our current value of x and subtract, and then we're going to have that ratio of f of x over f prime of x. Now my f of x is in y1, so I'm going to go to vars. And on your calculator, you'll have to scroll over to the right to yvars. You can see choice number 1 is then function, and there's choice number 1, y1. So there's my f of x divided by. Now this part's going to look really funky, but it actually will work. Remember to do the numerical derivative on your calculator. It's math 8. So I'm going to hit math. And I could scroll down, but since it is choice 8, I can also just quickly hit the 8 key. And see, it looks funky, but it will work. So in the parentheses, I need to tell it that my function is in y1. So I'm going to do vars y1. And this is also going to look funky because I'm going to say x equals x. The calculator's smart enough to know these two x's are kind of serving different roles. The first x before the equal sign, that's telling us the variable in the function, and then after the equal sign is the value that we want that variable to equal. And remember, up above we told it x was 1. Now don't hit enter yet. I just scrolled to the right real quick See how my cursor's down there right now by the X? I'm going to scroll to the right, just hit the right arrow, so I'm next to it. This is going to give me a new value for X, and I want it to store into X. There's a lot of X's here. But now, when I hit enter, it's calculated Newton's method for me, the first iteration, and it's put that value in for X. And here's the beauty of it. All I have to do is hit enter again. It's using that new value for X. It's going to calculate a second iteration for X, and now it's stored that into X. And I just have to keep hitting enter. And now you can see it's settled on a value. And then that's it. So it's a cool little trick you can do with the calculator. If we go back here, you can see there's the values there. 77827, 77827. Pretty cool. All right, that's it. So I should be back on Monday. Thanks for being great, and I will talk to you guys later. Bye.